Okay, let's dive right into this explainer. If you've ever looked out the window of a commercial jet and just watched those massive engines hanging off the wing, you know they generate some serious thrust. But how they safely manage the fuel to actually create that thrust, well, that is an absolute masterclass in engineering. We're looking at one of the most complex, high-stakes systems in aviation, the turbine engine fuel system.
Think about this for a second. What actually stops a jet engine from literally melting mid-flight? It's a kind of terrifying thought, right? The survival of the turbine blades, and really the entire engine itself, relies completely on a perfectly calibrated flow of fuel. The system doesn't just feed the fire. It has to automatically correct for changes in ambient temperature and pressure as the plane climbs and accelerates, all to make absolutely sure the turbine blades never exceed their strict temperature limits.
It is the ultimate balancing act. On one hand, you have a rich blowout. This happens if the fuel increases way too rapidly. You might think more fuel just equals more fire, but ironically, dumping in excess fuel can actually cool the mixture below the combustion temperature. It literally suffocates the fire, or causes a violent compressor stall. On the flip side, there's lean flameout. That's the other extreme, where fuel drops proportionally below the air quantity, completely starving the fire. The engine has to perfectly thread the needle between these two catastrophic extremes without a single hiccup.
So, how did engineers solve this life-or-death puzzle? To understand that, we're going to trace the evolution of fuel controls through 4 distinct stages: the nervous system, the mechanical era, the hybrid safety net, and finally, today's FADEC digital future.
Let's start with part 1, the nervous system.
Before any fuel control system can even do its job, it needs a crystal clear picture of what's happening inside that engine every single millisecond. It's constantly bombarded with data. You've got the pilot's power lever position, engine RPM for each spool, compressor inlet pressure and temperature, burner pressure, and compressor discharge pressure. Just imagine having to calculate and adjust for all those rapidly changing variables continuously just to keep a plane safely in the sky. By sensing these exact parameters, the system figures out the precise thrust needed for a given fuel flow.
To handle all that incoming data, the aviation industry evolved through 3 distinct eras of fuel controls, starting out purely hydromechanical, evolving into a hydromechanical and electronic hybrid, and finally landing on the absolute gold standard we use today, Full Authority Digital Engine Control, or FADEC for short.
That brings us to part 2, the mechanical era. The biggest challenge early on was figuring out how to compute all this vital engine data long before we had modern computers tucked into our pockets. Back then, we relied on pure hydromechanical controls. There was absolutely zero electronic interface assisting in computing or metering the fuel. None. Instead, the system was driven directly by the gas generator gear train of the engine itself to physically sense engine speed. These early controls had 2 sections, computing and metering. The computing section would mechanically figure out the right fuel flow based on physical pressures and temperatures, and then hand the actual job over to the metering section.
The sheer mechanical complexity of this era was honestly staggering. We're talking about an absolute maze of cams, evacuated bellows, and servo valves that physically metered the fuel without a single microchip in sight. Operating these things was incredibly complicated, and frankly, the fuel metering just wasn't anywhere near as precise as what we have today. It was a mechanical marvel for its time for sure, but it definitely had its limits. Moving on to part 3, the hybrid safety net.
As aviation technology advanced, engineers realized electronic controls could handle way more inputs with far greater accuracy. This led to a brilliant transitional phase in engine design, a hydromechanical and electronic hybrid system. It was basically a fail-safe masterpiece operating in 2 separate modes. Normally, in automatic mode, a remotely mounted electronic engine control, or EEC, runs the show. It handles thrust setting, speed governing, and acceleration limits, perfectly controlling the fuel metering via a highly sensitive torque motor. But here's the genius part. If the electrical system or the EEC ever failed, the pilot could just flip a switch to manual mode. The hydromechanical system completely takes over control of the engine, usually at a reduced power, just to make sure you can keep flying and land safely.
In this dual setup, the main goal is to pressurize, meter, and deliver atomized fuel. Fuel comes into the control unit through a 200-micron inlet filter screen and is metered out to the engine by a servo-operated valve, which is powered by a fixed-displacement vane fuel pump assembly. It really goes to show how early electronic controls still relied on having that robust, heavy mechanical system attached directly to the engine as the ultimate backup plan.
And finally, Part 4, the FADEC digital future. Today, we've reached the absolute pinnacle of this evolutionary timeline, where that physical mechanical safety net has been completely removed. FADEC stands for Full Authority Digital Electronic Control. By definition, this is a system where a dedicated computer has complete 100% control over fuel flow based entirely on electronic sensor inputs. Most modern turbine fuel controls are rapidly shifting to this standard. Why? Because it's unbelievably accurate. It can sense a multitude of engine parameters and schedule fuel in ways purely mechanical systems couldn't even dream of achieving.
A true FADEC system has no hydromechanical fuel control backup system. Think about what that actually means. That is a massive leap of faith in modern engineering. We now trust the computing section, the EEC, so implicitly that the mechanical backup is just gone entirely. The EEC gathers all the data, computes it, and sends the commands. The fuel metering valve simply reacts. No physical overrides, just pure digital authority.
This digital brain acts as the ultimate processing hub. The Electronic Fuel Control Unit, or EFCU, pulls in aircraft signals like airstream differential pressure, right alongside engine signals like fan spool speed and interturbine temperature. It instantly digests all of that, respects all the predetermined engine operating limits, and outputs the exact electrical signals needed to schedule the fuel. It's essentially a flawless digital conductor, leading an incredibly complex mechanical orchestra.
And what's truly amazing is how scalable this tech is. FADEC isn't just for one specific type of plane. It's the universal digital standard used on practically everything. From the small auxiliary power units, those APUs hidden in the tail of the plane that might use a tiny 10-micron inlet filter and a 70-micron screen, all the way up to the massive main propulsion engines powering commercial airliners. This digital authority is the industry baseline for safe, efficient, and surge-free combustion across the board. So, as we wrap up this explainer, I want to leave you with this thought. Next time you fly, as you're taxiing down the runway and you hear those engines roar to life, are you going to be thinking about the invisible computer keeping that engine's fire perfectly balanced? It's a relentless split-second balancing act happening right outside your window, constantly guarding against a rich blowout or a lean flameout, all just to keep that fire burning perfectly so you reach your destination safely. It kind of changes how you appreciate the journey, doesn't it?